So, Assalamu alaikum. So this is again a second video or summary for the second week in the for the first order differential equation. So in the last summary, I reviewed from the start of the differential equation that we said that it's either ordinary differential equations or partial differential equations. And in the ordinary differential equations, we can classify them as first order differential equations, second order differential equations, and higher order differential equations. And in the first order, we studied separable, linear, Bernoulli, and exact. In the last summary, I covered separable, linear, Bernoulli, and actually here also like the not exact or the integration factor or integrating factor. So this video is a quick recap of what we do in exact differential equations. So here as we said in the lecture that again a differential equation that can be written as bunch of x's and y's times dx plus n bunch of x's and y's times dy equals 0. Actually, any first order differential equation can be written in this form. However, if we can write this, or if this condition is satisfied, partial m, so this part here, the partial y tends to equal partial n by partial x. In this case, this differential equation is exact differential equation. In this case, this is like a check to check this differential equation if it is exact or not. Now, if so, if it was exact, then we have a way to solve it. The way that we solve it, so I will rewrite this again. This differential equation is actually generated as, so this m, the m itself is partial f by partial x dx plus partial f by partial y dy equals 0. So this is another way of writing this differential equation. It's just another way. This differential equation here is another way that can be written here, where m is just this and f is just this. So in order to solve this differential equation, we need to recover the f. We need to find the f of x and y equals 0 or equals c. This is the solution, a relationship between y and x that satisfies this differential equation. How we could find this f? That's the solution. The f is the solution. So f, we can find f in actually two different ways. So in finding f of x and y, we can integrate the m, which is this part here, according to dx, but we need to add a function of y. And we explained in the lecture why we need to add a function of y, because this was a partial derivative according to x, so the constant might have a y. And this is step number 1. Step number 2, whatever we got here, we do the partial f, which this one, the one that we got here, partial f per partial y, and this, we will make it equal n, or it should equal this n here. So from this is step number 2. This condition here, or this equation here, will give us information about g dash of y. G dash of y will equal some other y's here, and then we integrate the G dash of y according to dy. We'll integrate whatever is here according to dy. The integration will cancel the differentiation. So this is G of y will give us, we can get some information about the y here after we calculate this integration. So this is one way of doing that. We could do like exactly the similar thing, but just we reverse. Instead of integrating the m according to dx, we can say that f x and y equal integrate n dy, but here we have to add g of x, a function of x. And then I guess you might guess that we're going to do partial f by partial x, and we will make this equal to m. And from this, we're going to generate g dash of x will equal some x's here. And you will find that this equation will lead to this. And then you integrate those x's here. I don't know, that depends on the particular problem that you're solving. Then here we can recover g of x will equal to whatever the results of integration here. And this is like a formal way of solving the exact differential equation. The exact differential equation is any differential equation that's written in this way, that can be written in this way, and it satisfies this condition. There is another way to solve the exact differential equation as well, which is easy in the case of the, like if m and n are easy to integrate, we can say that we can get something called f1, which is integrate m dx. And also we get f2, which is integrate n dy, without adding constants or anything. And then once we get this, and we get this, we say that the f that we want is f1 union f2. And that's it, equal constant. So we kind of add, the union is addition of this and this, but eliminate the copies that are repeated. The copies that are repeated, we just eliminate one copy of them. So this is also, and we explained this in the lecture clearly, I guess. So this is the exact differential equation. So now, when we have a first order differential equation equal f x and y. So when you're given a differential equation that has first order derivative and bunch of x's and y's, so you would think, like, you should ask yourself here, is it separable? If yes, then solve it. If no, ask yourself, is it linear? If yes, solve it. If not, then move. Is it Bernoulli? If yes, then solve it, and so on. I mean, if this doesn't work, this doesn't work, this doesn't work, then we ask ourselves, is it exact? If yes, then solve it. If not, what if it doesn't satisfy any of these? You cannot solve it as separable, you cannot solve it as linear, you cannot solve it as Bernoulli, and also it is not exact. Then there is one more chance to try, which is the integrating factor. Some differential equations that are written again in this form, some differential equations that are written in, again, a function of x and y dx plus a function of x and y dy equals 0. When you do partial m by partial y, it does not equal partial n by partial x. So it is not exact. And we make sure it's not any of the above methods as well. So in this case, we might be able to convert this into exact. So we can, in some cases actually, not always, in some cases, we can convert the above equation, differential equation actually, into exact. So we can convert this into exact. How? With multiplying this differential equation with a mu, a function. So we're gonna multiply mu times m, x and y, dx, plus mu times n, x and y, dy equals 0. So, and this function here, which is we call integrating factor, will make this part, the derivative of this part, partial all of this, according to y, will equal to partial all of this according to x, which will turn it into exact. But the issue is that how we could find the mu. So mu could be, if there is a mu, so mu can be a function only in x, e to the power integration b of x, or it could be function only in y, which is e to the power integration b of y. The mu of x, I mean, this is if we can find this if the following is satisfied. What is that following? Is that the b of x, we can find the b of x, which is partial m by partial y minus partial n by partial x. Remember, you got those already, divided by n. If all of this is only function in y, then this is the right integration factor. Similarly here, if partial n by partial